Hello everybody and welcome to our video on motion in space. So for this video we're just going to do a couple examples that don't really cover new concepts per se. They're just going to take the concepts we've already learned and apply them to some problems, involving exactly what this title is, motion in space. So let's start with a fairly straightforward question. A moving particle starts at an initial position, r of 0 equals 1, 0, 0, with initial velocity, v of 0, is I minus j plus k. Its acceleration is 4ti plus 6tj plus k. Find its velocity and position at time t. So the same old laws of motion and their relationships apply once we put things into the vector realm. So if we want to know what the velocity of something is, well, we need to integrate the acceleration function. And of course, we can integrate that component by component. So that gives us 4t squared over 2, which is 2t squared I, plus 6t squared over 2, which is 3t squared j, plus 1k integrates to tk, but we also, when we integrate, we're going to get a constant of integration, but we should keep in mind that that constant is actually a vector-valued constant in this context. Okay, so what is that vector-valued constant? Well, in this case, if we notice, if we take v of 0 and plug it in, we get 0, 0, 0, and c. So v of 0 equals that vector c, and we already know what that vector v of 0 is, right? V of 0 is I minus j plus k. So this is 2t squared I plus 3t squared j plus t times k plus 1i minus 1j plus 1k. So now we're just going to combine each of our components. And what do we get? We get 2t squared plus 1i plus 3t squared minus 1j plus t plus 1k. Okay, so that gives us our velocity function, and now we need to find our position function. Well, again, position is the integral of velocity. So here we get 2t cubed over 3 plus t I plus 3t cubed over 3, which is just t cubed, minus t, j, plus t squared over 2 plus t, k. And don't forget we've got an integration constant here, so we'll call this one d. Now, again though, if we evaluate at 0, all of these terms are going to be 0, so we're just going to be left with that vector d. So that tells us that d is our initial position, which actually, the problem was using r for the position vector, so I should just change that back to r. Okay, so r of 0 equals d. Okay, so let's go ahead and set that up. So if I'm adding d, I'm just going to kind of skip a little step here instead of rewriting out all of d. D is the vector 1, 0, 0, so this is going to be 2t cubed over 3 plus t plus 1, I. And then we're adding 0 to these other two vectors, vector components, so they're not going to change. And that's it. That gives us our position function for time t. Okay, so let's go ahead and move on to one more example. Now, this one's a little bit trickier. Mostly, it's a matter of the setup. If we figure out the setup, the computation isn't too bad. So, a projectile is fired with an elevation alpha and an initial velocity, v naught, assuming that the air resistance is negligible. Another nice typo. The air resistance is negligible, and the only external force is due to gravity. What? Okay, there we go. I guess it just wanted me to have a comma there. Okay, so the only external force is due to gravity. Find the position function r of t of the projectile. What value of alpha maximizes the range? So first we'll have to find the position function, and then we'll have to figure out this next part here. Now we do know how to express or what the gravitational constant should be, right? 9.8 meters per second squared, or the acceleration due to gravity, we could say. But it's actually going to be a lot easier and a lot cleaner if we just write it in terms of g. So throughout this problem, I'm just going to leave this expressed as g rather than try to write this number 9.8 every time. So first, to understand this question, let's draw a picture. So a projectile is fired, and when it's fired, it has initial velocity vector, v naught. But of course, it's not going to travel in a straight line. The force of gravity is going to take this projectile, and it's going to force it into a parabolic arch. So the angle that's formed initially with this vector is alpha. And what we're assuming is that we have this initial velocity that's just a constant vector. And that initial velocity, the only thing that acts over time on the projectile is this external force due to gravity. So, what does that tell us? Well, it tells us a couple things here. So the first thing is the acceleration, the magnitude of it is g, which is 9.8, but we'll just say g. And that tells us that the acceleration vector looks like what? Well, the acceleration vector is only pulling down on the object, so there's no x component. And that means there's just negative g for the y component. Okay, so then what's the velocity vector going to be? So v of t. Well, we integrate each component. We get 0, negative g times t, plus some constant. But we know that v of 0 is v naught, right? And when I plug in 0 here, I just get 0 plus c. So v naught has to equal c. So the vector v naught. For now, I'm just going to leave that written in the general form, vector v naught. Now, when we integrate this to get our position function, we'll have 0, negative gt squared over 2, plus, now since this is a constant valued vector, the integral is just that vector times t. And then we have some constant here again. But our initial position, r of 0, is actually 0 in this case because we've placed our starting point at the origin. It's the 0 vector, so d is going to be equal to 0 here. All right, so the only thing we have left to do here at this stage is just find a more precise expression for v0 so that we can combine these vectors together. Well, that's not too difficult. What do we know? We know that v0 is the vector that travels in the direction of alpha with magnitude v0. And the direction of alpha vector is given by cosine of alpha sine of alpha. So v0 can be expressed as the magnitude of v0 times cosine of alpha, and then the y-coordinate is the magnitude of v0 times sine of alpha. So if I'm multiplying that by t, this becomes the vector, magnitude v0 cosine alpha times t, and magnitude v0 sine alpha times t. And so if I add these two vectors together, what do we get? We get magnitude v0 cosine alpha t. And then here we get negative gt squared over 2 plus magnitude v0 sine alpha times t. Okay, so that's a pretty good start. This is our general position function of the projectile. Now the question says, what value of alpha maximizes the range? What value maximizes the range? Okay, so we have to think about that. What does that mean? Well, first, let's just define what we mean by range. We mean the distance that this projectile can fire, and we'll call that little d here. And this distance along the x-axis occurs when y equals 0. So we're going to start by setting y equal to 0 and solving for the time. So we get negative gt squared over 2 plus v0 times sine of alpha times t, all equals 0. If I factor out a t here, I get t times negative gt over 2 plus the magnitude of v0 times sine of alpha equals 0. So of course that gives the solution t equals 0, but it also gives the solution for this being equal to 0. And I'm going to skip a little algebra here, but what does this give me? So when I subtract that to the other side, both will be negative, which will cancel, and I'll get left with the magnitude v0 sine of alpha divided by g and multiplied by 2. Now, what we're trying to maximize isn't the y value. We're trying to maximize the x value. This d is the maximum value of x, so we want to plug this time into x. So that implies x equals the magnitude of v0 times cosine alpha times 2 magnitude of v0 sine alpha over g. And I'm going to rearrange this a little bit. I get v0 squared over g times 2 cosine alpha sine alpha. And the key here is recognizing this old formula. So this is your double angle formula for sine. And so if we recognize that, we can substitute that in here and get sine of 2 alpha. And this is what's going to let us figure out how to maximize x, because we know that the maximum value of this expression is 1. And it occurs when alpha equals pi over 4, because then 2 alpha will be equal to pi over 2, and sine of pi over 2 is 1. So that gives us the angle for the maximum. Alpha equals pi over 4. All right, well, that's going to be it for this section. Thank you for watching.